Hello my fellow developers. In previous episodes we learned how to use Postgres as a vector database. First, we figured out how to use the pgvector extension to store and query embeddings. And second, we discovered how to use an HNSW index to boost the performance of our similarity search operations. And today we are making a step forward. If your generative AI application becomes a hit, then at some point you can run out of storage, memory, compute and other resources that are given to your single server Postgres instance. Which means that you need to find a way to make your Postgres scalable and distributed. How do we achieve it? Let's dive in. Alright my friends, let's do a quick recap of what we have already built so far. That's our generative AI application that recommends various Airbnb listings for those traveling to San Francisco. So imagine that you're heading to the city and you would like to stay near the Salesforce Tower and in a walkable distance to the AT&T Stadium. That's your user prompt, you click the search button and the service will recommend you several options. The whole information is stored in Postgres, including embeddings for Airbnb listings. You might be wondering, where is my Postgres instance is located? Well, it's not a secret, it's running locally in a Docker container. And if you go to the application source code and click on the properties file, you'll see that by default the application connects to that local instance. Presently, the standalone Postgres instance is more than enough for our application. Why? Just because we have a small data set. We have a little bit more than 7,500 Airbnb listings and embeddings that we generated for their descriptions. But once you start storing millions and dozens of millions or even more embeddings in your Postgres instance, then you can easily come short of resources. Let's do a simple calculation. We use the OpenAI model to generate embeddings for our dataset, and every embedding is a multi-dimensional vector. In our case, the vectors have 1536 dimensions, and every point in a vector is a 4-byte floating number. Now, let's do some math. Now we store 7,000 Airbnb embeddings in Postgres, and those embeddings will consume around 33 megabytes of storage space. But once you start storing millions of embeddings, then you need to allocate more than 5.7 gigabytes of storage. If you store tens of millions, then you need to have 57 gigabytes of storage. If you store billions, then start thinking about terabytes, my friend. At some point in time, you can easily run out of resources that are available to a single Postgres instance. How do we scale Postgres? How can we make it distributed? Well, Postgres was designed for single server deployments, but its ecosystem is so rich that you can find several options that can make Postgres scalable and distributed. One of those options is YugabyteDB. Let me do a quick intro for you, my friend. YugabyteDB is a distributed SQL database that is built on Postgres. Literally, it's Postgres that scales and never fails. Usually you run YugabyteDB in a multi-node configuration spanning several availability zones, regions or data centers. And that's exactly what we need for our generative AI application. YugabyteDB will be able to distribute our embeddings across several database nodes, and by doing that we no longer will be capped by storage, memory and compute resources of a single database server. So let's see what we need to do to switch our Airbnb recommendation service to YugabyteDB. Same as Postgres, YugabyteDB is fully open source and there are many deployment options that are available to us. But as a developer, I'd like to have it running on my local laptop. That's why I will start a 3-node YugabyteDB cluster in Docker. Let's move forward, starting the first node, proceeding with the second, and deploying the last one. Alright, as you can see, Docker says that I've got a 3-node YugabyteDB cluster running locally. That's exactly what I need. Also, I can always check the state of the cluster by using a special UI. Just go to the localhost and use the port number 15433 to see the state of your cluster. As I said, we started a 3-node instance. What's about data? Let's go to the databases tab and you can see that there are no any databases and tables yet. What we need to do next, we need to migrate data and schema from Postgres to YugabyteDB. And there are several options to do that. You can use YugabyteDB Voyager, that's a special migration tool that was created for YugabyteDB, or you can use other services and tools from the Postgres ecosystem. What approach will we use today, my friend? Well, as long as our data set is relatively small, I will simply recreate the application schema on YugabyteDB end, and then I will load the dataset from a CSV file that was created from the Postgres data. So step number 1, let's connect to our local YugabyteDB instance. We are in. We don't have any tables or relations yet. It's easy to address. Let's recreate the application schema that is located in the Airbnb listing SQL file of their application project. So we enabled the pgvector extension, and we also created the Airbnb listing table. If we run the /d command right now, we will find the table in the database. How about this table size? Let's do the count star from Airbnb listing. We don't have any data yet. Let's copy the data from the CSV file that was generated from Postgres. And this command will also copy all the embeddings that were previously generated using the OpenAI model. So it's done. We've got the data in our database. If we check the size right now, that's how many records we have. Now let's jump back to our YugabyteDB UI. That's the view of our cluster. If we navigate to the Databases tab, you will find the YugabyteDB database, and under it you will locate the Airbnb listing table. And that table is sharded. It's distributed across the 3-node cluster. That's what we wanted to achieve. And the last final step, my friend. Let's see how much effort it will take to migrate this Airbnb recommendation service from Postgres to YugabyteDB. Let's jump back to our application project. In fact, as long as YugabyteDB is distributed PostgreSQL, we don't need to introduce any code level changes here. All we need to do is to update the following application properties file. Let's do this. YugabyteDB still runs on localhost, so nothing to change here. But we need to adjust the port number. YugabyteDB listens on 5433. And we also need to update the name, user, and password. The database name is Yugabyte. Guess about the user, it's also Yugabyte. And the most secured password in the world, Yugabyte as well. Done. That's it. That's all we need to do to migrate from Postgres to Yugabyte. Now let's stop our application backend. And next, let's restart this backend using YugabyteDB as a database. Okay, backend successfully connected to Yugabyte. Jumping back to our application UI, and let's execute the same prompt over their YugabyteDB cluster. You've got the same recommendation that we've got with Postgres before. Congratulations! With that, our generative AI application is no longer capped by resources given to a single server instance. If necessary, we can always run the app over a distributed PostgreSQL cluster, known under the name of YugabyteDB. And stay tuned for the next episodes in the Postgres as a vector database series, my friend. Bye bye now.